something rather odd happened on the way down here because before I left Hattiesburg, I printed out my notes, which was really just a section from a book, and I'm pretty sure I put it in my bag. And upon arriving here and getting this out, I do not see my notes at all. I'm not sure what happened, so I'm gonna have to do this a little clumsily and like flip back and forth for little tidbits. But that would be less cumbersome if that's okay. Or okay, yeah. All right. At least that way, at least it's almost the same as if I brought them here. Okay. All right. So, first, I should have gotten an email about this. So, practice final exam has been posted. So, lectures page under the December 5th entry. So, okay. All right. So, right here, so you can see the problems. Okay. And at the end, just like the midterm formula sheet, front and back this time. Like table of Gauss quadrature nodes, for instance. Now, what I have here are a total of 8 problems. So, so from the corresponding 8 problems I have from real tests, I will choose a subset of those. And hopefully all of you know what this means. I will choose a proper subset of those. For the undergrads, and then a proper superset of those for the graduate students. So, something like that, yes. Yeah, so give the practice ones a try. Now, some of these I have not covered yet, but at this point, anything to do with interpolation, differentiation, integrations of problems 1, 2, 3, 4... 1 through 4 from the last chapter. Problem 5 is what I did on Tuesday, and problem 6 and 8. That's tonight's stuff. The Newton's method, secant method are next week, and that'll be it. That'll be all the material.
The week after Thanksgiving, are we just going to be doing review?
Yeah. So Tuesday will be review. Thursday class time is the test. Yes?
Are you recording?
I am, yes.
Okay. I thought I should remind you.
Oh, thank you for reminding me. Since apparently there's hardly anybody in Hattiesburg to do so. So, okay. Okay. Yeah, in fact, I'll probably have to ask as many of you feel like it to remind me the rest of the way, just so we don't have another mishap. Okay. And then I'll be sure to post the diary from a little MATLAB activity I had last time was posted, and it'll be same thing for tonight. Okay. So even before the review, if you can take some time to try out some of these problems, and there'll be time to ask questions during class. And then that'll give you an idea as to which problems and how many should show up in a real thing. And there will be a lightning round, same kind of thing, about 10 questions or so on differentiation, integration, solving nonlinear equations. Okay. All right. So now, last time we saw one method for solving a nonlinear equation or finding a root of a function that's bisection. guaranteed to work if you know it changes sign on interval, but slow. So now we're going to look at a very different method for solving equations. Okay, so suppose that we rewrite the equation we want to solve, fx equals 0. So we want to find some root of a function f of x in this form, x equals g of x. Now, there are many ways to do this, and I'll talk more about how we choose a way to write this equation. But I'll just give an example. I could always set g of x equal to x plus 5x f of x. So if I have it, so if I make g of this form, where preferably phi is some non-zero function. So that way, fx equals 0 if and only if x equals g of x. So you go ahead and solve this equation instead of that one. Now, how exactly does this get us anywhere? Well, for one thing, it leads to an extremely simple algorithm for solving this rewritten equation. So I'll just sketch it out now in pseudocode. So first we choose an initial guess, which I'll call x0. And then we'll repeat the following until we get some kind of convergence. Okay, and it's just, hold on. Gotta make sure tab's right. Okay. Okay. So this algorithm is one step. All we have to do is xk plus 1 okay. All right, is equal to g of xk. Okay. Oh, I didn't need to make that bold. Okay. All right. And then k equals k plus 1. All right. All right. So initially, I would set k equals 0. So this is all we do. We have our initial guess. We plug that into g and get our next iterate. And then we plug that in. And then so plug x1 into here, get x2, x2 into here, get x3. We keep going. And hopefully, these iterates will start to converge to one another. So once xk plus 1 minus xk is sufficiently small, so consecutive iterates are so close to each other that they might as well be equal, then we can say that the iteration has converged. So if this iteration converges, and I should mention this is a big if, then then x star, which I'll refer to as the limit as k goes to infinity of x k, is called a fixed point or stationary point of g of x. So the algorithm is therefore fixed point iteration. So all it does is, from your initial guess, it will find a fixed point of G if convergence is achieved. So we have a very simple algorithm, a very simple framework at least, but we just have a lot of questions to answer before we can really use it. Okay, so given g of x that's obtained from f of x in some way, we have these questions to answer. And at least I'll be able to give some answers. Is there a fixed point at all? How can we be sure? Are there some conditions under which we can be certain that there's a fixed point of G, which is therefore a root of F? If so, is it unique? Can we establish that? And it turns out we can. And if it is unique, will the iteration converge to it? That's not assured, but there will be some conditions that we can state. And finally, if convergent, how rapid is the convergence? Is it possible, even if this iteration is successful, can we come up with a different G based on the same F? Because here I could come up with G of this form. I could choose phi to be anything, preferably non-zero. And this will be a valid equation. But maybe I could choose G in such a way, whether it's of this form or not, that will lead to more rapid convergence. So how can we speed up convergence? Right. So the rest of tonight is about getting some answers to these questions. But first, I'm going to show you some examples about what happens when we try this iteration, what can go right and what can go wrong. Okay. So first example, x minus cosine x, so that'll be my f of x. And I want to find a root of that. So f of x equals 0 is rewritten as x equals cosine of x. Okay. All right. So what I will do is I'll try to solve this equation by fixed point iteration. And okay, do I have this here? Oh. All right, for an initial guess, let's see. I'm going to choose 1/2. So that'll be my x0. Okay. All right. All right, so I'm going to carry this out in MATLAB, and let's just see what happens. So I'll start a diary here. Okay. So I'm going to set x equal to 1/2. So I'll just do all of this at the prompt. And then I'll let x equal to cosine of x. So 1/2 is going to be substituted into this function, cosine. And what do we get? Okay, so we get 0.8776. And now I'm just going to repeat this command over and over. So we see it's bouncing around a little bit. There's some oscillation here. But what I'll do, I'm going to do several of these commands in rapid succession. And notice the values are getting closer. Because at first we had nearly 0.9, then 0.6, then 0.8, then 0.7. So there's a lot more swing in the values than there is now. Now they're all hovering around 0.74. And sure enough, now we have all the same value. It's at least to 4 decimal places, it has converged. Let's see more decimal places. And there's still some change there, but we do see convergence. So I substitute this value into cosine, and the same value comes out. So if I have x minus cosine x, which is my f of x, it's quite small. So in this case, fixed point iteration was successful. It took some time, a certain number of iterations to get to the root, but let's see, if I were to count how many iterations, at least to get 4 decimal places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20. Okay, so about a little more than 20 iterations to get to 4 decimal places. Not that great in terms of speed, and before class is over, you'll see why. Okay, so that's one example. Okay. Now I'm going to do another. So f of x is equal to x squared minus x, plus 3/16. Now what I'm going to do, since this is a quadratic polynomial, I can get for roots. Has roots at, so I'll put this polynomial, okay, so So my polynomial will be x squared minus x plus 3/16. And then I get the roots. All right, so 1/4 and 3/4. Okay. So it has roots that's 1/4 and 3/4. Equivalently, the equation x equals x squared plus 3/16 has 2 fixed points at 1/4 and 3/4. Okay, so what I'm going to do is pick an initial guess. We'll give you 1/2, which happens to lie between these two. And let's see what happens. So I'm going to make a function handle. G is a function of x, and it'll implement the formula x squared plus 3/16. And I'll set x equal to 1/2. So now I can do x equals g of x. Okay, so it starts decreasing, and we can see that it's heading towards the first of the fixed points, 0.25, and it's converging fairly rapidly. Okay, if we look at the error from 34 to 17, notice the error is decreasing by a factor of 2. In other words, the iteration is about as fast as bisection, and I've already mentioned that bisection is kind of slow. Now, what about the other fixed point? So I'm going to choose x. Now, if I chose x equal 1/2, which was halfway in between, it still went to 1/4. So I'm going to choose something very close to 3/4, 0.74. So you'd think, okay, if I plug this in, it should converge to 3/4. But let's see what happens. It starts decreasing slowly, but now it's decreasing at a faster rate and heading towards 0.25. So it's like that other fixed point of 3/4 was repulsive in a way. Now let's try this. Slightly greater than 3/4, so 0.76. I'll try it again. It's increasing and increasing and going off to infinity. So that's not good. So, wow. This is pretty terrible, in fact. Although it makes sense because whatever value we're plugging in, it's once x gets greater than 1, we plug it into x squared plus 316, it's going to square it. And that's exactly what we're seeing here. It's the order of magnitude is doubling. So what we saw was if the initial guess is in the interval 1/4 to 3/4, iteration converges to 1/4. But if the initial guess is greater than 3/4, iteration diverges. Okay. Now, I'll do one more. Function f is x plus natural log of x. Now, I should point out, by the intermediate value theorem, fx equals 0 for some x in this interval, 0.5, 0.6. And the way I can confirm that, I'll define my function handle to be x plus log of x. So log in MATLAB is a natural log. Use log 10 if you want log to base 10. So I'll plug in 0.5, and we get a negative value. And 0.6, positive value. So by the intermediate value theorem, this function is continuous. Therefore, some solution exists in between. So here's what we can do. We apply fixed point iteration to x equals minus natural log of x. Just by taking fx equals 0 and moving ln x to the other side. With initial guess, the midpoint of this interval. Because we already know we could use bisection on this interval and get a root. But let's see how fixed point iteration does. All right, so so g is equal to minus natural log of x. All right, so we're still inside the interval, but now we're outside. That's not good. And now it's going further and further out, and now it's complex because it attempts to take the natural log of a negative number. This one right here. So this didn't go well at all. So let's revisit this. So how can we rewrite this equation to get a new equation of form x equals g of x that might work? So if we have this, x equals natural log of x, what might we do to manipulate this equation to get something that's fundamentally different that we can try again? What would be something we could do to both sides of this equation? Yeah, take the exponential. Of both sides. So I get, stop it. So I get e to the x is equal to e to the minus natural log of x. But that's the same as e to the ln of x to the minus 1. But what does that simplify to?
1 over x.
Yeah, 1 over x. So e to the x is 1 over x, or we can write that as x equals e to the minus x, because taking reciprocal of both sides. So let's try this. X equals e to the minus x. So I'll have the same initial guess. Nope, that one. And now I'll redefine my g. E to the minus x. So now, do x equals g of x. Staying in the interval. And it's looking a lot better. Still taking its time converging. Okay, now it's definitely converging. We already have like 6 decimal places, 7, 8. Okay, so we can say that the iteration was successful in this case. Okay, but what we don't know is why. What's different about this iteration? Is there any property that this g of x has that the other one doesn't, so that we have some guidance? Right now, we're just kind of fumbling about. Same thing here. Why, in the case of a function that has multiple fixed points, did it converge to one and not the other? What was different about those 2 fixed points that caused one to attract iterates and one to repel them? So we need some answers. So that's where convergence analysis comes in. So first, we address the question of existence of a fixed point. So there's a theorem for this by the Brauer Fixed-Point Theorem. G of x has a fixed point, meaning x star is equal to g of x x star. Okay. In an interval AB, if the following is true. G is continuous on AB, and this is the particularly important condition. G maps the interval AB into itself. And what I mean by that, if x is in the interval AB, then g of x is also in AB. So that's one way we can be certain that a solution at least exists. Okay. And in fact, I won't go into it now, but, well, actually, I think I signed it. Yeah, I signed it as a homework problem. The proof is short, and it comes from the intermediate value theorem. Okay. Okay. So basically trying to show that a certain function is a different sign at one endpoint of the interval than at the other endpoint of the interval. If you show some function is opposite signs, then it must be 0 somewhere in the interval. The same principle that bisection is based on. Really? Okay.
Intermediate theorem.
Oh, wait. You proved the intermediate value theorem? Or oh, okay. But now you're going to use that to prove this.
Huh?
But now you're going to use that theorem to prove this. So I guess that proof may not help you, but yeah.
Oh, that won't. It's like it's like 2 interval AB.
Yeah.
On the interval, you're trying to find Just basically trying to find those interval value.
Yeah.
It's kind of like what you do.
Okay. Oh. So I see these things come up in multiple classes.
Yeah. Quite a stuff I do in here, I use back in there.
Okay. Well, good. All right, so that settles the question of existence. But what about uniqueness? Okay. So if function g of x has a fixed point, also interval a, b. So in other words, if it satisfies these conditions for a Brauer fixed point iteration, and satisfies a Lipschitz condition, AB, meaning the following, that g of x minus g of y is less than or equal to some constant L times x minus y for any xy in the interval AB. Where the number L is called a Lipschitz constant. And we also require that L is less than 1. Then the fixed point is unique. All right, so it must satisfy the conditions for existence. It must satisfy this Lipschitz condition with a constant that is less than 1. And there's some terminology here. We say that function g is a contraction on AB. Okay. So what I've just stated here, so if these conditions are satisfied, then by another theorem, which I won't have you prove, contraction mapping theorem, not only is the fixed point unique, it is guaranteed that that fixed point iteration will converge to the fixed point, the unique fixed point, for any initial guess, x0, in the interval AB. Okay. All right, so that's what we really want. We want g to be a contraction. So if we take our original equation, f of x equals 0, that we want to solve, to find the root of f, and we write it in some way in the form x equals g of x, if we can do that in such a way that we can ensure g of x is a contraction, then we know that fixed point iteration will work. But the problem is, although it's nice that we have a condition like this, a condition like this is not easy to check. But fortunately, I can give a condition that that is easier. Okay. So by the mean value theorem, we have this. If I take the ratio of these expressions, so I have x minus y in the denominator, and I have g of x minus g of y in the numerator. And that is less than or equal to L, but this expression is equal to G prime at some unknown point. And we want L to be less than 1. Okay, where C is between X and Y. Therefore, C is also some point stop it. So C is also some point in AB. So instead of trying to check for this for all X and Y in AB, we could check this. Is the derivative bounded above by some constant less than 1 on the interval AB? So by yet another theorem, by the Fixed-Point Theorem, if G prime, an absolute value, is less than or equal to some constant L, which itself is less than 1, on the interval AB, then we have a unique fixed point. And again, just like in the contraction mapping theorem, point iteration is guaranteed to converge for any initial guess, AB. So, like the bisection, we have some reliability of a method, some guarantee it'll converge. It's just that the conditions are a bit harder to satisfy. In bisection, all we needed was that a function is negative at one endpoint and positive at the other endpoint of AB. Here we need the derivative to be small. We also need G to map the interval AB into itself. All right, so now that we have these conditions, let's revisit the examples that I gave earlier to get an idea of the behavior that we saw. Okay. So our first example, x equals cosine x. Well, g prime of x is equal to minus sine x. And an absolute value that's at least guaranteed to be less than or equal to 1. Now, at the fixed point, and I'll need to scroll back through MATLAB to refresh my memory as to what that fixed point was. Okay, so about 0.7391. Okay, so I'll take the last iterate I got. That was as converged as possible. So here's my fixed point. So I'm going to plug this into the derivative. Okay. So the derivative is minus sine of that. All right, so at least it's less than 1 in absolute value. So what that means is if you choose initial guess, if you choose an interval that's close enough to this, like you're avoiding pi over 2, because at pi over 2, the derivative is going to be equal to 1. So, for example, on the interval 0 to 1, cosine x is in 0 to 1. So it satisfies the existence condition. If I choose any x in 0, 1, cosine will also be in 0, 1. It will not go negative. Keep in mind these are in radians. Also, the absolute value of g prime of x is less than or equal to sine of 1. But what is sine of 1? That's 0.84. So in other words, this value, so therefore, cosine x is Lipschitz continuous on 0, 1 with Lipschitz constant sine of 1, which is less than 1. So that is why we can be sure in this case that fixed point iteration converged. But the smaller the Lipschitz constant is, here it is here, the faster the iteration will converge. Now, to explain that, okay, Okay. So it is less than 1. Works on the interval 0, 1. But convergence is slow because L is not much less than 1. Because what we have here, consider the error xk minus x star of a fixed point. Okay, so I have the following. If I look at the difference between k plus first iterate, that is, now xk plus 1 is g of xk. But x star is the same as g of x star, because it's a fixed point. But by the mean value theorem, this is equal to g prime at some unknown point in between, which I'll call ck, times the difference of x values. So this is how the k plus first error relates to the kth error. The error is multiplied by the derivative. That's why the derivative needs to be less than 1 in absolute value, to make sure the error shrinks. The smaller g prime is on the interval AB, faster the convergence. Okay. And I'll be able to use this in a later example to show how we can change g to speed up a convergence. Okay. All right. So that's the first example I had. The second example was x equal to x squared plus 3/16. So in that example, g prime of x is equal to x. But g prime at the first fixed point, therefore, is 1/2. So that's less than 1. While the derivative at the other fixed point, 3/4, is 3/2, greater than 1. That's why that fixed point is actually called an unstable fixed point. So if a derivative at the fixed point is greater than 1 in absolute value, fixed point will not converge to it. The iterates will be sent away. So how a derivative behaves on a fixed point is paramount in understanding why fixed point iteration succeeds or fails. And in the last example, x is equal to minus natural log of x. G prime of x is equal to minus 1 over x on the interval 0.5 to 0.6. But if we're taking 1 over these values, because they're less than 1, 1 over that will be greater than 1. So that's why fixed point iteration with this g was not successful. So when this happens, try rewriting x equals g of x by taking g inverse of both sides. So what does that give you? We get g inverse of x, of g of x, on the left side. On the right side, we get g inverse of g of x. But that equals x. So now we get the equivalent equation, x equals g inverse of x. Now, if x equals g of x failed, how do we know that trying with g inverse will succeed? Now this came up last time, that the derivative of G inverse is equal to 1 over G prime of G inverse of X. So when you take the inverse, you take your reciprocal of a derivative. So if a derivative of G is too large, taking G inverse will take a reciprocal of that and make it small enough. So if you try a certain G of X and it fails, due to derivative being too large, this is guaranteed to give you a successful iteration. Now, you may not be able to get G inverse. I mean, we could in this case, but so really what you're doing is you're taking this equation and you have this X isolated. What you do is you solve for the other X. And that's how you get this modified equation. All right. So that gives you an idea as to how to choose a G that will work. All right. Now, I have another example. This is actually my favorite one. Let's suppose our function that we want to find a root of is x minus cosine x minus 2. So we write in this form, x is equal to cosine x plus 2. So this cosine x plus 2 is our g. Now, given what we know about cosine, can anyone tell me what are the smallest and largest possible values of this function, cosine x plus 2?
3.
Yeah, 3 and 1. So this g of x, stop it. Okay. All right. That g of x maps the interval 1, 3 into 1, 3. Now, actually, g of x maps any interval to inside 1, 3 because those are the smallest and largest possible values. So g has a fixed point in the interval 1, 3. So let's try initial guess to the midpoint interval of 2. Now, what I'm going to do is I will try fixed point iteration in MATLAB again, but I'm also going to plot the iterates. But I also want to plot the function. So I'm going to choose x. Well, okay. For plotting purposes, a lot of points between 1 and 3. I'll make sure I have no figure windows open. Okay, so then I'll plot this and then cosine of these values plus 2. Okay, so this is what the function looks like. So notice for x between 1 and 3, the values of g of x go from 1 to like 2.5 something. So a fixed point does exist. I'm also going to plot the line y equals x. Okay, so that's the line y equals x. So here we have g of x, here we have x. When x equals g of x, or the graphs intersect, that's the fixed point. But my initial guess is over here at 2. So what I'll do is, all right, so I'll set x equal to 2, and then g I'll define to be cosine x plus 2. So now I'll have x equals, so I'm going to plot x, g of x, and I'll use a black circle. So there it is on the graph. Okay. And then, okay, so that's roughly 1.6. Now, the next thing I'll do is I'm going to plot a line. that goes from this point, and I'm going to go to the left to the line y equals x. So I'll go from so x at 2 to g of x, and my y-coordinate will be g of x in both cases. I'll make that line black as well. Okay, so it goes here. And then, this is my new iterate. So x equals g of x. So 1.58 something. Now, I'm going to plug that into g. So in other words, I'll be going from here up to the blue curve. Okay. So x, x, and then x, g of x. So now I go up to the curve. All right. So now, where am I? My new y value is roughly around 2 again. So I'm going to make a plot a point there. All right. So this is my initial guess was 2. This is my second iterate, and it's on the other side of a fixed point. Now I'll do the same thing as before. I can take this point and go to the line y equals x, a horizontal line. So I have x, g of x, g of x, g of x, black, and it goes over there. Okay. Now, now that I've done that, I'll update my x. And notice it's just a little less than 2, 1.98. So now I will go down to the curve. Okay, so I've almost formed a box, but not quite. It doesn't exactly close. All right, but notice my third iterate is very close to my first. Okay. So now, like before, I'll go to the line y equals x. I can just repeat the same commands. Okay, and then update my x. 1.595 versus 1.583. Not much change. Okay, so then go up to the curve, plot the point, and I can keep going. Okay. What? What noise?
It's like a, yeah, it's like a little, almost sounds like a little coin noise.
Oh.
It's from there.
Yeah,
Oh, okay. Yeah. So, alternating iterates are on opposite sides of a fixed point, and you can see that convergence appears to be happening, but it's extremely slow. The actual fixed point looks to be right around like 1.8 or so, maybe a little less than that. So it's going to take forever to get there, although we are going to get a nice picture out of the deal if I were to keep this going. And actually, this is how fixed point iteration can always be depicted. That you plug into your function g, then draw a horizontal line to y equals x in whatever direction, mark the point there, then take that new x and go up or down to the curve, horizontal line to y equals x. You keep going back and forth. It happens to create a spiral in this case, but other times it's a different sort of sequence of line segments. But from the behavior, we actually see that it actually suggests a way to speed up convergence. Because if both of these are on opposite sides of a fixed point and slowly approaching it, maybe the average of these two would be closer. So that's what I'm going to do. I'm going to define a new g. That will be the... okay. So convergence is very slow, iterates on opposite sides of a fixed point. Instead, we try x equals h of x, where h of x is the average of two consecutive iterates. So here's what I'll do. H of x is equal to 1/2 x plus g of x. So that would be equal to 1/2 x plus cosine x plus 2. Okay. Now, let's go ahead and try that. So h is a function of x, and it'll be x plus cosine x plus 2 all over 2. And my initial guess, I'll set it back to 2. Okay. So now I'm going to mark in red okay, x, h of x, red circle. Okay, now I haven't plotted h of x, but notice the y value. It's right around 1.8. That seems to be closer to fixed point already. So now what I'll do is x equals h of x, all right, 1.79 from 2, and I will do it again. Whoa! That's pretty dang close. So let's try it again. Not much change this time. And it's pretty much hit it almost immediately. All right, so whole lot better. So why is that? Let's look at a derivative. All right, so g prime of x is equal to minus sine x. Now, I pretty much have a fixed point here already. So if I do minus sine of x, it's almost 1 in absolute value. So no wonder the iteration was so slow. So we have absolute value of g prime at the fixed point is approximately 1. So the slowness of that is explained. Meanwhile, h prime of x is equal to 1 minus sine x all over 2. So if I plug a fixed point into here, okay, 1 minus sine x all over 2, 0.01. That means the error is reduced by a factor of 100 every iteration. So you basically gain 2 decimal places per iteration. Okay. So h prime, or absolute value of h prime, at the fixed point. All right. So that explains why it performs so much better. Now, in general, we have a following. Fixed point iteration converges linearly. So remember, last time I gave it different types of convergence: linear, superlinear, quadratic. Bisection converges linearly, and the constant is 1/2. Where fixed point iteration, it is the absolute value of g prime at the fixed point. And that comes from what we saw earlier. New error is equal to the derivative at a nearby point times the old error. So the error is being amplified by this g prime. So that's why g prime, we need it to be less than 1. But the smaller it is, the closer it is to 0, the better, as we saw in this example. But But what if G prime is equal to 0? So let's take a look at that. All right. Okay, so I have, again, xk plus 1 minus fixed point, which is equal to g of xk minus g of a fixed point. And by Taylor expansion, that's equal to g prime at x star times the previous error. But the next term of Taylor expansion is 1/2 g double prime at x star times xk minus x star squared, and so on. So if g prime is 0 at the fixed point, this whole term is gone. So that means the new error is equal to this constant times the old error squared. In other words, quadratic convergence. So to summarize, if g prime is 0, but g double prime is non-zero, then fixed point iteration converges quadratically with the asymptotic error constant c is equal to g absolute value of g double prime at the fixed point over 2. So convergence is much more rapid in that case. If this derivative was also 0, then it would be cubic convergence, and the error constant would be absolute value of g triple prime at the fixed point over 6, and so on. So however many derivatives of g are equal to 0 at the fixed point determines the order of convergence. So most cases it will be linear. Now whether it's faster or slower than bisection depends on this value. So like the last example I did of like cosine x plus 2, that convergence was slower than bisection. But then I changed g of x to h of x, and I got something that was literally 50 times faster. Okay. Now, but it would be nice if we could get quadratic convergence more often. And that takes me to my last point. Okay. So we define the solution of equations by relaxation, or solution of equation fx equals 0 by relaxation. Stop it. Okay. By fixed point iteration x equals g of x, with g of x is equal to x minus some constant f of x. Now, I won't go through all of the theory here, but what I can tell you is that if f prime at the solution is non-zero, then it is possible to choose lambda so that this iteration is guaranteed to converge for an initial guess x0 sufficiently close to the root. Because if f prime is non-zero, then it's possible to choose lambda so that the derivative of g is guaranteed to be between -1 and 1. And we can actually find out how small and large it can be depending on how large and small the derivative of f can be. Okay. Now, okay. But what I can also say is that the convergence is linear. So really, the proof comes from homework problems, but I did not assign those problems. But it can be shown the convergence is linear with asymptotic error constant C is equal to 1 minus lambda f prime at the solution. Okay. Now, okay. Of course, we would like this to be as small as possible. So, ideally, we would like to choose lambda to be equal to, well, how should I choose lambda so that convergence will be as rapid as possible? If this determines how my error is amplified or damped from one iteration to the next, will be a good choice of lambda to make convergence fastest. Because the smaller c is, the more rapid the convergence. So how should I choose lambda? How can I make this small as possible? If I could choose lambda to be anything. Yes? Yes, 1 over f prime at the root, which would yield quadratic convergence, if we could do that. How come we can't act in practical terms? How come we cannot do that? What's stopping us from choosing lambda to be that value? Sorry, what? Oh, no. In fact, we're under the assumption that the derivative is non-zero.
But C, can C equal 0?
Well, C would be 0 with that choice, which is what we want. Yeah, we want C 0. We don't know x star. It's a value we're trying to get. Yeah. So we'll do the next best thing. Instead, we can vary lambda from iteration to iteration, choosing lambda k to be 1 over f prime of f of x k. This leads to what is called Newton's method, which does converge quadratically, even though, so in spite of the fact that we're choosing an imperfect lambda, but if the iteration is converging, this lambda that we can get is converging to the ideal lambda. So that's why, and I'll show this on Tuesday, quadratic convergence can still be made to happen. Okay. Um, so, and this goes to what I was doing in a previous example in a way, but it's just based on observations of the iterates. And actually, that happened by accident. I was just looking for another example of fixed point iteration. I just made one up, tried it, and saw how the iterates were behaving. It's like, oh, that's interesting. What if I took the average? I had no idea, but I suspected it would work, and it did. It actually led me to go further and try to generalize that idea to try to choose an optimal G. And when I get to the secant method, I'll be able to say more about how that went. So fixed point iteration by itself, in a general case, it's not necessarily that much greater than bisection. Although if you're able to choose a nice G for which the derivative is small near where you think the solution is, then yes, it is far more effective. But that's not easy to do. So fixed point iteration may not be the best method in its own right, but it creates a powerful framework for developing better methods. And that, like in this case, it leads to a derivation. Well, there's many ways to derive Newton's method, and I'll show you another one on Tuesday. But this whole idea of solving an equation by successive substitution, it's really one of the most powerful devices out there for solving difficult equations. Now, for those of you who have taken differential equations, MAP 285, depending on who taught it and what they felt like covering, if they covered the existence uniqueness theorem, the proof of that uses fixed point iteration. That a differential equation is rewritten in the form of a fixed point iteration, and the iterates in that setting are called Picard iterates. And it's shown that that iteration, that G, if you will, is a contraction. So all the ideas I've just been talking about for fixed point iteration for an ordinary nonlinear equation were applied there for a first order differential equation. And for many other kinds of equations, this idea of fixed point iteration is used. It's really a whole branch of math in its own right, fixed point theory for different kinds of problems in higher dimensions and so forth. Next semester I'll cover a multi-dimensional version of fixed point and also Newton's. So that's what I'll get into next week, where we have the much more rapidly convergent methods for solving equations. Newton's method and the secant method. They're all based in some way on fixed point. Okay, so all right, so that's today's material, but we have some time for any homework questions that you might have. Even if there are not many people around to ask them. But at least they have a video.
Did that fifth guy ever show up?
What?
Did that fifth guy ever show up again?
Oh, he dropped a class. Yeah, and I'd forgotten about that. So, yeah. So everybody supposed to be here has been here.
He come on first day, he don't come back. He was in 2 classes with me, he didn't come back to either. I think he don't come.
Well, I guess it's good I haven't lost my touch at scaring people off, but
I feel like the real analysis scared me pretty good.
it would do that, yeah. It's,
It'll hurt your heart. That class.
Unfortunately, my very last semester is when I have to take real analysis. So
It hurt my heart.
senioritis kicking in.
eh.
It will crush you.
It hurt my
Okay,
heart.
so will.
I
Give
remember
me sleepless nights.
I remember sitting there until like 3 a.m. just like sketching out like proofs and just like not I'd write it like 3 times because I couldn't figure it out. I feel so bad.
It will shatter you.
Any questions at all on homework?
On 9.7.5.
975. Okay. Whoops. Okay.
The head tell you to use the weighted mean.
Right.
And you're supposed to use that and the error, but it
Yeah, so both items play a role. So if you're using the idea that the error in the integral is the integral of the error, in this case, the integral of the interpolation error. So if there's any portion of that error, okay, so if I flip back to this theorem, if there's any portion of this error which you know for a fact will not change sign on the interval AB, then that serves as like a weight function. So you can leave that inside the integral, pull the rest out, and evaluate it at an unknown point. So that's just what the weighted mean value theorem for integrals is saying.
and the weighted part is then x minus x naught squared instead.
Yeah, so something that you would know does not change sign. Yeah. Any other?
A 9.7.1.
971. Okay. Okay.
So you're gonna set up a system of nonlinear equations
Uh,
solve for unknown, right?
Right.
Wait, 1.2.
Yeah, so you'll set this with 2, n equal 2, equal to the integrals of 1 x squared, x cubed. But for example, like what always happens in this kind of direct construction, the first equation you get is that the sum of the weights is equal to b minus a. So right away, that lets you eliminate one of the weights. And one thing that's convenient for this example, on the interval minus 1 to 1, the integral of a odd function on a symmetric interval like this minus 1 to 1 is 0. So you're setting is equal to 4 different integrals, but 2 of the integrals are 0. So that it just helps simplify the algebra a little bit. It was also convenient. Well, I have this on the formula sheet. So actually, this is what you're supposed to get. Although, if you look at the Wikipedia page for Gauss quadrature, and it shows this same table, except they are in radical form. So, like the exact answers. So you can check your work that way for the 2-node case.
So we should get the top part.
Sorry, what?
And 2, but I think we're in here, we go up to 3 here, right?
Well, the degree is 3, but the number of nodes is only 2. Because you have, x1, x2, w1, w2. So x1, x2, and if the weights both turn out to be 1. All right. Any more? Okay. Oh. anyone who doesn't have questions is welcome to go. So.
So the final, if I heard that right, the final is on the Thursday after Thanksgiving break?
Right.
Okay.
Yeah, December 5th.
So for 9.74, right? You just basically.
9.
I just need to know because I'm heading up to Detroit, like, and I'll come back like 3 days before last week. And I need to bring
Oh, wait, which problem?
9.74. 9.74.
Yeah, because I'm not gonna get to
Wait,
like, I'm not
I
gonna
didn't
take
assign that
it.
one.
Oh, it's fine.
Yeah, 5. Yeah.
Oh, yeah.
Oh yeah.
Let's say 4's a killer.
Yeah. It's fine.
I don't have a choice. You have a good night.
You do. Is anybody still in a room in Hattiesburg?
Oh, they gone.
Oh, you left everything on. Dang it. No, if I was up here, I'd shut everything off.
Oh, remember I was telling you that one time I sent you a code for one over, but you say you never get the code.
Oh, hold on. Okay. Oh, for which? Okay, hold on. Let me stop the video here.